You're standing at the base of a massive concrete dam. Right behind that wall, millions of tons of water. It looks completely still, perfectly peaceful. But there are actually these incredibly powerful, invisible forces trying to push that wall down, literally every single second. Welcome to this explainer. Today, we're diving deep into the physics of static fluids. These are the absolute foundational forces that we, as civil engineers, have to master if we want to design resilient infrastructure. Let's get into it. So, how exactly do engineers calculate the precise moment a static fluid will break through a massive barrier? Because, there's this common misconception out there that a fluid at rest is just a fluid without power. But actually, nothing could be further from the truth. In reality, static fluids exert relentless, highly calculated pressure. And understanding exactly how those forces behave, well, that's exactly what separates an engineering marvel from an absolute disaster. Section 1. Foundations. Pressure at a point.
Okay, so let's dive right into this. Pascal's law. This is our absolute bedrock. It basically dictates that the intensity of pressure at any point in a fluid at rest has the exact same magnitude in all directions. Now, why is this the case? Well, because in a static fluid, shear stress, that friction that causes layers of fluid to slide past one another, that is completely zero. Because the fluid isn't moving, the only forces acting on a microscopic little point of water are normal pressures, and they are pushing perpendicularly and equally in literally every single direction.
Now, take a look at this free body diagram of an infinitesimally small wedge-shaped fluid element right out of the text. I know, it kind of looks like abstract geometry at first glance, but it's pure mathematical proof. By taking the forces acting on the x and z axes and keeping in mind that the fluid is totally at rest and perfectly balanced, the equations resolve perfectly. They show us that pressure strictly equals pressure no matter which face you're looking at. Regardless of the angle of that wedge, the normal forces just balance right out to zero. And that brilliantly illustrates our next core principle, the hydrostatic law. Check out these interconnected containers. Notice how they have wildly different shapes. Some are wide and cylindrical, others are narrow or bulbous. But if you look at the free water surface across the top, it's perfectly level across the board. This visually confirms a huge concept for us. The pressure at any point in a static liquid does not care at all about the shape or the volume of the container. It's driven strictly by vertical depth and the specific weight of the fluid. That's it. Section 2. Forces on plane surfaces. Before we jump into the math, I really want to emphasize this critical concept just one more time. In a static fluid, shear stress is absolutely zero. Since our fluid is just resting there, we don't have to worry about tangential friction dragging our walls down. So when we're calculating the forces on our plane surfaces, we literally only need to worry about the normal, perpendicular compressive forces pushing straight into the barrier. All right, so how do we actually calculate that total force? Well, here's the classic textbook formula. Total force F equals rho times G times A times H bar. But let's translate this into an intuitive engineering reality, right? Rho times G, that gives you the specific weight of the liquid. Multiply that by A, which is the total area of your plane surface, and then you multiply that by H bar, which is the exact vertical depth down to the geometric center of gravity of your barrier. Essentially, the total force pushing on your barrier is just the total weight of a column of fluid acting directly at the surface's center of gravity. Section 3. The center of pressure. Okay, this brings us to a concept that honestly trips up a lot of novice engineers, the center of pressure. We just calculated the total force using the center of gravity, but here's the catch. The actual force doesn't push exactly at that geometric center. This visual brilliantly illustrates why. Look at the inclined plane here. Notice those horizontal arrows representing the fluid pressure pushing against the wall? At the top, up near the water surface, the arrows are pretty short. But as we go deeper, vertical depth increases, and according to our hydrostatic law, so does the pressure. So the force vectors get dramatically longer at the bottom of the plane. Because all that pressure is so heavily concentrated down at the bottom, it essentially pulls the overall balancing point of the force downward. Let's see how this actually builds out on a precise structural diagram. The real physical application of the total resultant pressure actually sits physically lower than the centroid. You can clearly see that distinct gap between the letter G, the geometric center of gravity, and the letter P, the center of pressure. And this is huge. If an engineer designs a support brace assuming the force hits at the exact geometric middle, well, they're going to vastly underestimate the tipping momentum at the base of the structure. So the big question, how do we find exactly where to place those supports? We use this formula. The depth of the center of pressure, we call that H star, equals the moment of inertia about the center of gravity divided by the area times h bar plus h bar itself. It mathematically proves exactly what we just saw visually a second ago. The center of pressure is always the center of gravity, plus an additional downward depth factor that's driven by the surface's moment of inertia.
Section 4. Forces on curved surfaces.
All right, so we've successfully engineered our flat walls. Nice. But now it's time to advance to the bus level of fluid statics. What happens when civil engineers need to design, say, the sweeping arch of a concrete dam or a massive submerged cylindrical pipe? So the crucial point here is understanding how our physics has to adapt. With plane surfaces, all those tiny microscopic pressure arrows point strictly parallel to each other. That allows us to calculate a single resultant force directly. Super easy. But on a curved surface, the angle of the wall is continuously changing at literally every single millimeter. The pressure vectors point in a million different directions, so no, we can no longer just sum them up into one simple perpendicular vector. Instead, to, keep our sanity, the total force must be resolved into distinct horizontal and vertical components.
Visually, it looks exactly like this. Over on the left, we've got the differential math. The text isolates a tiny slice of a curve, taking the resulting pressure dF and using trigonometry to break it into a horizontal force dFx and a vertical force dFy. I know, it looks highly theoretical, right? But pan over to the image on the right. That is a cross-section of a colossal curved dam. The differential calculus you see on the left is the exact language engineers use to guarantee that that mountain-sized structure on the right doesn't just shatter under millions of gallons of pressure. Fortunately, the textbook actually distills all this complex calculus into an incredibly intuitive two-step procedure. Step 1. To calculate your total horizontal force, Fx, you simply calculate the pressure force acting on the projected vertical area of the curve. Just imagine shining a giant flashlight horizontally directly at the curved wall. That flat vertical shadow it casts, that's the area you use for your calculation. Really simple. Step 2. For the vertical force, Fy, it's exactly equal to the total weight of the liquid supported by the curved surface, extending all the way up to the free water surface. Section 5. Engineering takeaways. Okay, let's quickly lock in these core principles before we wrap. Number 1, always remember shear stress is completely zero in static fluids. We are strictly dealing with compressive normal forces here. 2, by the hydrostatic law, pressure depends entirely on vertical depth, period. 3, the total force on a plan relies on the center of gravity, but because pressure increases with depth, the actual pivot point, the center of pressure, is practically always lower. And finally, number 4, for curved surfaces, you absolutely must split your forces into a horizontal component based on the projected flat area and a vertical component, which is based purely on the weight of the fluid resting right above it. At the end of the day, mastering these static fluid forces isn't just about passing a civil engineering physics exam. It's really the absolute first step to engineering the resilient, fail-proof infrastructure of tomorrow. I mean, every time you see a soaring retaining wall or a massive hydroelectric dam, you are literally witnessing Pascal's law and the hydrostatic equation hard at work, holding back the tide. These static forces are immensely powerful for sure, but they are mathematically completely within your control. But what happens to our equations when that static water